Swayam Prabha. Digital India. Educated India.
Another very practical example is that the one for the plates. For example, if I have a thin plate, if you imagine this as a plate over here, and it's a thin plate Y, compared to my X and Y direction, my Z direction is extremely small, right? So this is a thin plate. So thin plates are typically loaded in plane. So you have the in plane loading. For example, you pull it like this. Thin plates never get this out of plane loading, because of which the plate might easily buckle. So the application of thin plates are mostly, you have these in plate kind of loadings which are there, right? So this is also an example where if you see this, if this is my XY plane over here, all the loads that I'm applying are along the XY plane. I do not have any load in this particular Z direction that is there, right? So as you can see within this figure as well, right? If suppose the face of this plate is the XY plane, all these forces that you are seeing act along the XY plane. There is no force along the Z direction that you have. So what does this essentially mean? So this means that if there are no forces along the Z direction, that automatically means that some of the stresses vanish. So because the forces are related to the stresses, or in other words, the stresses are actually related to the forces, right? So if you don't have forces about a particular direction, the stresses automatically vanish, right? For example, the bottle example and the range example which I was showing you, in that particular one, you're not applying any shear about the Z direction, you're not applying any normal force about that particular Z direction. So essentially your sigma Z, right, your tau xz and tau yz, any force that has to do with the Z direction, it essentially vanishes. So if for the generalized state of stress, remember the small element that we were looking at which had the stresses along all the directions, now if you impose this condition, this somehow becomes like this. I have my sigma x, I have my sigma y, I have my tau xy, but along the Z direction, this is my Z direction, along the Z direction I do not have a sigma z, I do not have a tau xz, I do not have a tau yz as well. So the generalized formulation that we looked at, how does that change now? Let's go and take a look at that. In the generalized formulation that is there, right, this was the generalized form of what we had. So now that if we do not have the sigma z and the tau xy and the tau xz, so as you can tell automatically that this particular element is going to vanish, because your tau xz equals to 0, your tau yz equals to 0. So this is also going to vanish, right? And in these three equations over here, which component is going to vanish? Well, none of the strains are going to vanish, because the strains depend upon the stresses in the other direction. So only within these equations, that particular component which only depends upon the sigma z, that is going to vanish, because my sigma z, remember, it is equals to 0. So here this component is going to vanish, right? In the second one also sigma z equals to 0, so this is going to vanish. And in the third one over here, sigma z equals to 0, so that is going to vanish as well, right? No, epsilon z is not equals to 0, sorry, I meant to write that this particular component over here, that your sigma z is essentially 0, right? So you say now the strains become kind of simplified, and if you come back and if you substitute over here, if you do the transformations, what you will find, as it has to corroborate with what you saw in the the generalized state of stress after you remove the sigma z, tau yz and the tau xz, that this is going to disappear, this is going to disappear, and if you come back and if you put the values over here, you will see that this particular component is going to disappear as well, right? If you come back here and you put the value of the epsilon z and the epsilon x and epsilon y, you can try doing that exercise and you will see that this one also disappears, right? So now that we have this one, the general set of equations, after we impose these conditions, you have a reduced set of equation, as you can there, right? So this is the reduced set of equation. That's what it looks like. Remember that for the expression of the epsilon x that we have over here, now you do not have the new sigma z divided by e, which we cancelled in the last page, right? You have a reduced equation for your epsilon y, and it's amazing if you see that your epsilon z, although you do not have a stress about the z direction, you do not have a sigma z, it still depends. And why? It depends, you have guessed it right, it depends because of the Poisson's ratio. It depends upon the Poisson's ratio. So it still depends upon the stresses along the x and the y, but through the Poisson's ratio, right? And among the shear strains, we have our tau xz and the tau yz vanish. So we only have your gamma xy, which is dependent upon the tau xy, right? And this is again the the transformation that you have been doing from the strains to the stresses. So this is just the transformation. You can put in the equations for the stresses that we looked at in the last page as well, and you will essentially get the same set of equations that is there. Okay, so that is the case of the plane stress problem. So from the name itself, since the word stress is involved, we are looking at the cases where about a particular direction your stresses vanish, right? Now from the name, now can you guess what is going to be a plane strain problem? Yes, you're right. Plane strain problems are those, from the word strain itself you can tell that about a particular direction the strains are zero. So previously we looked at about a direction the stresses were zero. Now we are going to look at the plane strain problems where about one particular direction the strains are zero. So let's look at some plane strain problems, right? So plane strain problems, as you can see from the figures over here, they have a wide range of engineering applications. For example, one of the very well-known applications of the plane strain problems are the dams, right? So if you take a look at this particular dam over here, dams are water retaining structures. See, this is the body of water which the dam is holding back, and this is your normal functioning roads or something that you have, and this is that entire dam that you're looking at, right? So in this particular dam that you have over here, right, if you think about the deformations of what is going to happen in this particular dam, see, it has at the left end over here and at the right end over here, it has these restrictions, right? So at the left end, it is kind of restricted. At the right end, it is also restricted over here. So it has essentially no movement, no deformation, no allowed deformations in those two directions, because the dam has to be in place, right? So there are no movement about that particular direction, right? The dam can have movement about the other directions, but essentially what you are doing, that you are restricting this movement as well as you are restricting this particular movement over here. The dam can still move about this particular direction and a vertically upward direction as well, right? It can have some amount of elongation, maybe due to temperature, due to the stresses of the water. You can have some amount of deformations about this direction, but no deformations allowed about these two particular directions over here. Essentially similar to this one, as you can say, this is just the hypothetical representation of the dam that you have, right? Here you have all the forces and the deformations in this one, but no deformations is allowed about this particular axis over here. Another example is gas-filled cylinders. When you have gas-filled cylinders along which the both ends of the cylinders are sort of fixed, you're not allowed to move. So suppose this is my z direction, you're not allowing any kind of deformations, whether, and remember, strains are related to deformations. So if you're not allowing any deformations about the z direction, that means you're not allowing any strains also along the z direction, right? What are the kind of strains that you're not allowing? You are not allowing the normal strains, you're not allowing the shear strains. So any kind of strains you are you are restricting about that particular direction that is there, right? So if we just go ahead and take a look again from the generic formula, if we just reduce it over here, now what we are looking at, that about say a z direction, if you take a look at our element over here, about this z direction, you're not allowing any amount of strain. So essentially your epsilon z becomes equals to 0, your gamma xz becomes to 0, and your gamma yz becomes equals to 0 as well. See, analogically, in addition to these two examples, another example which I can give you, remember when we were looking at the thermal stresses, right? When we're looking about the thermal stresses, you had this, bar. Now if you see this one, right, if this is my xy plane over here, so this is my, say, x, and this is my y, and say this is my z direction that is there. Sorry, I probably misspoke, right? So if this is my z direction, my x direction is going to be about, say this is my x, right? This is my z, and this is my y, right? So when you are heating this bar, and if you have it clamped over here, if you're heating this one, right, then in that particular case you're going to have maybe expansion about this particular, you can have expansion about the y axis, you can have expansion about the x axis over here, but about the z axis, imagine if this is the z axis, since it is clamped, you're not allowing any movement, right? So all the strains, the epsilon z which you are having along these two z axes over here, they are restricted. Your tau xz is your gamma xz is restricted, and gamma yz is also restricted, right? So now that you have over here, now as you can tell that we can go back to our generalized set of equations, and we can cancel some of the strains, and we can see what is a consequent effect on the stresses that you are going to have, right? So again, coming back to the generalized form, now that we know that my entire this epsilon z, since I'm not allowing any epsilon, this entire thing is going to vanish, right? This thing is going to vanish as well, and this thing is going to vanish as well, right? So these three equations go for a toss, right? We are still going to have this one and this one. So my strain vanishes, so do my stresses also vanish? Maybe not, because my stresses are also dependent upon the other kinds of strains which are there, right? So if we just go back and if you take a look at the reduced set of equations, remember, as we just marked in the previous page, our epsilon z vanishes, our gamma xz vanishes, and gamma yz also vanishes. The other strain quantities are there, and as we did, this is simply a transformation. You can apply, or you can input your epsilon z and gamma xz and the gamma yz in the previous equation. You will essentially get the same set of the transformed equations, right? So these are the two categories of problems which are there, which are the plane stress and the plane strain problems. And what we just looked at are several of the engineering examples where you will see that several of the practical life scenarios or the practical life problems can be sometimes reduced into the plane stress and the plane strain problems. You will learn more about these things in some of the advanced classes that you would take when you talk about plate theory or shell theory and so on. You will see that some of those problems can be reduced to these plane stress or the plane strain problems that we have over here. We are slowly reaching the end of our chapter on axially loaded members, and the last topic that is remaining within this particular chapter relates to the concentration of stresses, right? So, and this is a very relevant, a very particular subtopic within this chapter. Why? Because you will see that concentration of stresses or stress concentrations typically occur in members where you have discontinuity, right? So if you have a member where which is which has a uniform thickness and in a good amount of length, and if you're applying the load, the stresses, the flow of stresses is very nice and smooth. But once you're coming and putting some cutouts, a very practical example of that when you are drilling pipes, drilling holes for pipes within a wall, right? You have this nice uniform flow of stresses within the wall, and now you're coming and disrupting it by making a cutout for a pipe. So how is the flow of stresses going to change because of this particular disruption? And you will see that these kinds of examples of the stress concentrations happens at n number of objects around you. I challenge you, if you just look around you, you will see n number of things where you have these holes and notches and these cutouts which affect the pattern of the flow of stresses, right? One example I can show you right now. For example, you see this calculator over here, right? In this calculator, it used to be a nice plain member over here, but now because of the keys over here, you would have these small holes and notches and cutouts. Now if I'm pulling this calculator, suppose these keys and all were not there, if I'm applying the load P, along both the ends. At every section I will have a P divided by A, where A is the area of cross section of this calculator which is there. But now that you have come and punched these buttons over here, you've essentially made holes in whatever is the material of this long of this rectangular plate over here. You have made these holes. So when I am pulling it, near the vicinity of the holes of each of these keys over here, near the vicinity of the keys, which is a member of the plate still, near the vicinities of the keys, I am going to have the concentration of the stresses which are there, right? So also remember that this whole discussion on the concentration of stresses, if you think about it, it goes back to some of the things which we discussed in our the topic 2 when we were discussing about when we were learning about sigma x's. If you vaguely remember that back that time we had talked about the Saint Venant's principles. And what did we discuss about that? It was that if we have this particular member, right, and if you follow my fingers through which I'm going to apply a load P, for example, right, if you follow this one, right, if you see near the vicinity of my fingers, so where my fingers are, this one and this one over here, if you just look at there, you see those areas somehow squishes, whereas towards the center, these vertical lines, take a look at the vertical line at the edge, this one and this one over here, compared to the vertical lines at the centers, right? So the vertical lines at the edge have this kind of a broken kind of a pattern because it's a lot of concentration of stresses, whereas the ones at the towards the center, they are still vertical and they move kind of closer to each other. So towards the ends you have this large concentration of the stresses, whereas towards the center you have the more or less the uniform stress distribution. So if I have to show this using an engineering diagram, it's something like this over here. Towards the end, at these particular points, you have the large concentration of the stresses, whereas, and this is what this point says over here, that concentrated loads result in large stresses in the vicinity of the application point. So these are the places where you have stress concentration, right? And the scientist who first worked on this one was Saint Venant. He was a French elasticity theorist and a mathematician who first studied this phenomena. He also actually had enormous amount of contributions towards providing solutions for the Navier-Stokes equation, right? So he was the first one to study this closely. And also you're probably wondering from this figure over here that if I have the concentration of the stresses at the very ends, at what distances do I have to move from this P such that my general formula, that sigma equals to P divided by A, remember that's the formula that is there, that sigma equals to the force divided by the area. It is a uniform stress formula, which is definitely not valid in this particular region, but at certain distances away, more maybe towards the middle of this bar over here, where your stresses have had a good enough amount of distance to sort of percolate through. The best way to imagine this is, suppose you have suppose you take a glass, right, and or a bucket of water, and you put a drop of ink right from the top. So when the moment the ink touches the surface of the water, you have a large, and suppose the color of the ink is blue. The moment the ink touches the surface of the water, you will have a large blob of blue color where the ink just touches, because it's very concentrated over there. And as you move, if you give it a certain amount of time, as you move towards the bottom of the bucket, you will see that the blue color more or less disperses and becomes uniform, right? So right at the point where the ink drop fell, you have a large concentration of the blue color, and as you move further away, the blue color sort of disperses through and becomes uniform. Very similar concept to this one over here. Here you see this load P over here, where this load is applied, you have a large concentration of the stresses. So sigma equals to P over A is not valid. The sigma equals to P over A, if A is the entire area of cross section you're looking at, it is valid at certain distances from the point of application of the load, right? So let's take a look at that, and this is what it says over here, that it becomes uniform at certain distances, and we will see what that particular distance is, and something which Saint Venant worked on back in the day, right? So if we are looking at the same example, and I am presenting you 3 sections, so let me mark these sections over here. So this is a section 1, section 2 and section 3. And as these three different sections, I am trying to look at what is the nature of the distribution of the stresses. Now if you see at section 1, which is at some distance away from the where the load is applied, I have the nice and easy that my stress is sigma f equals to P divided by the area of cross section, which is H times T over here, right? Sigma equals to P divided by A, where A is the H times T. Right. Now if you go to, let's jump over to section 3, which is very near to where the load is being applied, and if you remember, that is where that squishing phenomena happens. At that particular point near to where your load is over here in these regions over here, you are going to have a jumping up of the stresses, and towards the edges you will see that the stresses are practically nil. So at the center you're going to have this kind of a distribution of the stresses. If you're looking at this entire section, this will be the distribution of the stresses that you will get, right? So at the center it is going to peak. So this is the average stress which I have already found out and I have marked over here. So towards the center you will have stresses which are significantly higher than the average stress, right? And towards the end it will probably drop off to 0. And if you look at an intermediate section, as you can guess, that your stresses are going to be sort of in between your 1 and 3 over here. So you're going to still have some peak at the center, but at the same time towards the end it's not 0 anymore. It will have some amount of magnitude. So you transition from highly concentrated regions to lesser concentrated regions to more or less a uniform region. Again, if you're talking about the ink drop kind of an example, your load sort of maybe starts to percolate, something like this over here. Eventually you percolate and you reach regions where your load distribution stabilizes and you have a more uniform distribution of the load. Now coming to the question that at what distance does the sense of uniformity prevail, it is found that, and Saint Bernard found this, that if you take a member with a H and a T, right, then at a certain distance, and suppose your H is the least lateral dimension, so here I mean that my H suppose is less than T, right? So at a distance of a least lateral dimension from the point of application of the load, the uniformity is going to prevail. So in those places you can apply the formula sigma equals to P divided by A over here, right? So at a distance H here, when you go, then you can apply sigma equals to P divided by H times T, where H times T is the area of the cross section of this particular rectangular block that you have over here. Right, now coming to some very practical examples of stress concentration, what can be some of the practical examples. One very practical example is this one over here, where you have in a plate you have a hole or a knot. Suppose this is your wall and you have drilled a hole for a pipe to go through, so you are going to have some concentration of the stresses over there, right? So let's go and do maybe a small experiment. So suppose this is your plate, right? Suppose this plane of this is your plate over here, and here I have drilled a hole over here, right? And what I am doing, suppose this plate is under, I'm just simply pulling my hands on both the sides, right? And suppose this plate I'm pulling it under with a load P and a load P over here, such that it is under normal stress, right? Now from this that you have over here, this A, B, C, D over here that you have, that where do you think that this paper that I have, where do you think it is going to fit, right, among these 4 points, right? So when I'm pulling it here, you can probably guess that it is going to fail at these points A and B. And let's try to do that. So if I'm holding this and if I'm sort of pulling it, you see it fails exactly at the top and these bottom points over here. So that is where, and it does not fail in other places. So what does that tell you? That tells you that there has been some concentration of stresses at these 2 points A and B when this was still intact, right? So this page essentially shows that. So if you have this plate with a hole over here, and suppose the length of this plate is, or the height of this plate is B, and let me maybe also mark the thickness over here. Suppose this thickness that you're looking at is T, right? So your and if you're cutting a section in this particular plate, if I'm cutting a section, and I am looking at the distribution of the stresses over here, right? So you will have and suppose my sigma average is nothing but the average stress. So suppose if I was cutting a section maybe somewhere over here, so my sigma average, which is also sigma nominal, sigma norm, as you can see over here, sigma nominal is equals to your P divided by your B times T, you know, the height times the thickness that you have over here, right? So near the edge, if I cut the section over here near this particular section, remember that in our case this failed, this essentially started to fail at these points, you know, A and B. So near these edges you are going to have a peak in the stresses, right? So here you reach the maximum stresses, sigma max, and towards the end your stresses reduce. These blue dotted line that you see over here, this dotted line is just the average stress, that is the P divided by B times. So towards the end you may have stresses which is slightly lesser than the average stress, but definitely where your notch starts, where your hole starts over here, in these two regions you're going to have the stresses which are high. And for the design purposes you actually have the charts like this, as you see on the right of your page over here, which essentially tells you that how to calculate those maximum stresses. So let's try to understand this chart first. So this chart, as you can see, it is your, in the y-axis you have a factor k over here, so you have k, and in the x-axis you have d over b, right? If this is not clear, let me just write it. It is d over b, right? And what is my d and what is my b? D is the diameter of the hole and b is this height of the plate that is there, right? And what is k? K is simply, through k you are, see, essentially you are trying to calculate the sigma max. K is nothing but your sigma, k is nothing but the ratio of the sigma max to the average stress or the nominal stress. So how do I calculate my sigma max? Sigma max is essentially, this is what you're trying to calculate the peak stresses which is happening at the regions which are tearing, so that you can, you know, you can provide sufficient thickness so that, you know, your failure doesn't happen. So sigma max is nothing but equals to k times sigma average or sigma nominal that you have over here. So this chart essentially gives you the relationship that if you have a plate with a hole over here with a particular diameter d and a height of that plate as b, right, and you know, depending upon this ratio d over b, how this factor k changes. So for, you know, very less kind of ratio of the d over b, so that means, you know, your b is sufficiently large. So if you have a very long plate and your d is, you know, very small thick, in those particular cases you're going to have, you know, stress concentrations which are going to sort of shoot up, whereas if you are, you know, moving further away along the horizontal line, you are going to have lesser amount of the value of the k over here, right? So this is the case where you have the plate with the hole or a bolt over there, right? Now another example, another kind of cutout that I can show you is something like this over here. So instead of the circular hole I have a quadrilateral kind of a cutout. So in this one again I have marked the points as a, b, c and d. Now as you can tell that if I have to, you know, pull this along both the sides, where is it going to rupture? It is going to rupture at a and b. So let's try doing that, right? So you see, as I pulled it, I, you know, sort of tore it at a and b. So the tearing starts right at these edges over here and it propagates towards the edge of the paper on the top. So you can have one more example of stress concentration, which is this one. That in this one you have this is the, you have probably seen this kind of equipment as well. This is a very, you know, one of very useful engineering toolkits where you know, those fillets you kind of use. Suppose you have a rough surface and you have tried to sort of smoothen it out, right? So in those ones what you have a sort of change in the cross section, right? A gradual reduction, not a, you know, a sudden jump. So as you can see, you have a height b and a height c over here. You have a gradual reduction which is marked by this, you know, this radii of curvature which has r over here, that particular radius. And suppose you have this thickness as T and T over here, right? So in this case also, as you can imagine, if you have a structure like that and if you are pulling in, the failure is typically going to try to happen about here. So you can, maybe in your home, you can make a a page cutout similar to the examples that we saw. You can have a page cutout, and as you will be able to see that the failure starts to happen in these particular regions as you are pulling with this force P. Now, as you can tell, for this one also, similar to the one with the circular hole, which is a practical example, the quadrilateral one which I just showed you, this one is not a very practical example. You rarely have these rectangular kind of a cutouts in civil engineering structures. Mostly holes to carry the pipes, or these kinds of the ones which you are seeing on this page over here, right? So here also you have these charts over here. So sorry, this is not the flat parts with circular holes, this is flat parts with shoulder fillets. I'm sorry about the error. With shoulder fillets. Fillets essentially mean these notches that you have, that is called a fillet, right? So for these cases, what you get is that, so this is again a similar chart. Remember that K that we looked at is simply this one over here, right? K is the ratio of the maximum stress to the nominal stress, where the nominal or the average is P divided by C times T. So you have this height over here times this particular thickness. This is the average stress occurring in this particular region that is there, right? And you have for your different values of B over C. Why? Because now you have a varying section. You have this B and a C over here. So this is for B over C equals to 2, and this is where you finally end up with B over C equals to 1.1. So for these varying ratios, you have these different lines which are there, and for what essentially each of these lines tells you that if you have a shoulder fillet where you have a wider section followed by a thinner section, and if you have the radii of curvature for that one, because the x-axis, if you see, the radius of curvature comes in over. If you have a very sharp transition, for example here, instead of this one being a smooth circular kind of a translation, if you had a very sharp drop over here, your stress concentrations are going to be even higher, right? So in those particular cases, you see that when you have very short kind of a very sharp transition, your K essentially shoots up at this particular regions over here, right? So these are some of the examples where you have stress concentrations, and you have these charts which are available in designer's handbook, so that every time you don't have to solve a solid mechanics or a finite element analysis problem. These are tabulated in tables, so the designers of these shoulder fillets, or when you're drilling a hole, you quickly look up those charts and that what is the material you need to provide, what is the thickness, and what is the height that you need to provide, right? So with this, we are going to wrap up this particular topic. I hope you enjoyed this topic. The next topic which we are going to move on to is completely a different nature of loading. So here we looked at members which are under axial loading. In the next topic, we're going to look at a completely different type of force. We're going to look at torques, right? So nothing to do with the axial pull. It is essentially a twisting, a particular, we're looking at the chapter of torsion, right? So with that, I would like to conclude this topic, and I will see you guys very soon.